welcome. Today in short text 331, we're going to talk about orthogonal basis. So what is an orthogonal basis? Well, let's say we have a vector space armed with an inner product, which we're going to call v comma w, as we've used in our previous video on the inner product. And if you haven't seen that video, you should probably take a look at that now. You can pause this video and go back to that one on the inner product. But once you know what an inner product is, then you know that if you have a vector space armed with such an inner product, you have what we call an inner product space. So let's say that in that space, we pick up a bunch of vectors that I'm going to call here v1 through vn, and let's call that set x. So it's just n vectors. And we say that those are bases, if you recall, when these vectors are linearly independent and altogether span our vector space V. So that means that any vector in our vector space V can be written as a linear combination of V1 through Vn. That means that the dimension of V is n by definition of dimension, and we say that this basis is orthogonal if and only if the inner product between the vectors is equal to 0 when they are two different vectors. Okay, so Vi comma Vj, or the dot product of Vi with Vj, is 0 if I is different from j for any value of I and j in our basis. So note that if also the inner product of Vi with itself is 1, we say that the basis is orthonormal since the vectors are normalized to be of length 1. This doesn't have to be the case, but it's usually very easy to just normalize the vectors as soon as you know that the basis is orthogonal. So a lot of the time when I talk about orthogonal basis, I will just assume that the basis has been normalized, and so the vectors are orthonormal to each other. Or we say that the basis is orthonormal. In that case, then we can write the inner product of Vi with Vj using this very convenient notation called the Chronicle Delta. And this Chronicle Delta is an object that has these two indices, I and j, and it's equal to 0 if I is different from j, and it's equal to 1 if I is equal to j. Okay, so if you were to write the values of I and j as a matrix, as a square, then you will have 1 on the diagonals and 0 everywhere else. If you're familiar with matrices, then you've seen the unit matrix, and that's basically what this represents. If you're not familiar with matrices, then don't worry. This is just then an object that has two indices, and when the two indices are equal, you get 1. If they're different, you get 0. So let's see some examples of orthonormal basis. So in R3, armed with the conventional dot product, then you have an inner product space. We can take X, our set of vectors that form a basis, to be the vectors, the unit vectors I, j, and k that usually are used to denote unit vectors pointing in the directions of x, y, and z. And that is already an orthonormal basis. Usually then those have components 1, 0, 0, 0, 1, 0, and 0, 0, 1. And you can easily see that the inner product of I with j is 0, j with k is 0, k with I is 0. But if you do the inner product of I with itself, or j with itself, or k with itself, then all of those are equal to 1. So this basis is already orthonormal. So let's see a more interesting example. Now in R2, again with the conventional dot product, you can form a basis with I and j, obviously, or with j and k if you want, that's totally fine. Usually we denote I in 2 dimensions with 1, 0 and j with 0, 1. But you can also pick a different basis, which would be unrelated to this one, ij, although one could transform one into the other by picking these vectors e1 and e2. And so this vector e1 has components by definition 1 over square root 2, 1 over square root 2, and e2 has components 1 over square root 2 and minus 1 over square root 2. And if you calculate the inner product of e1 with e2, you will see that it's indeed 0. So these two vectors are orthogonal to each other. And moreover, the magnitude of e1 is 1 and the magnitude of e2 is 1. And so you see that we have also in this case an orthonormal basis. I should say at this point that this series is meant for my students at the University of North Carolina at Chapel Hill. But if you find this series helpful, whether you're a student in my class or not, please consider liking and subscribing, as it would really help the channel. If you're not a UNC student though, and you're looking for a tutor in physics or math, either in English or in Spanish, you can contact me at shorttext331@gmail.com, or you can leave a message in the comments section below. Now, why do we define this orthogonal basis? Isn't it enough to just have a basis? And for many applications, it is enough to just know that you have a basis, that a basis is a basis. But in many cases, it's really convenient, it's very nice, it's very useful to really have an orthogonal basis or even an orthonormal basis. So suppose that we have one such basis, then we know that any vector in our space can be written as a linear combination in this way of the vectors in my basis. So here the vectors in my basis are v1 through vn, and the linear combination is formed with these coefficients a1 through an. Now, if you take the inner product of v, our vector v, with v1, then by using the properties of the inner product of linearity, you can see right away that this expression using the linear combination shown here becomes a1 times the inner product of v1 with itself, plus a2 times the inner product of v2 with itself, with v1, and so on and so forth, all the way through to an and the inner product of vn with v1. Now, by virtue of the basis being orthonormal, in fact, just orthogonal, we see that these coefficients here are 0. So we're left with just this one term. So you see the inner product of v with v1 leaves us just this one term. And if v1 with v1 is 1, we assume the basis is normalized, then the coefficient a1, you see, can be extracted simply by taking the inner product of v with v1. Why is that useful? Because if you want to express your vector v in a particular basis that may be convenient for your system of interest or for whatever you're describing, then you will need these coefficients, a1 through an. And you say, how do we calculate those? Well, you calculate them by taking the inner product of v with the corresponding vector in your basis. And so that's why this is useful. And so however you define your inner product, if your basis is orthogonal with respect to that inner product, then you can always play this game and say a1 here is simply the inner product of v with v1, and that goes here. What about calculating a2? Well, it's the inner product of v with v2, and so on and so forth. So the inner product allows us to calculate those coefficients. And then we can write in complete generality, again, as long as the basis is orthonormal. So I assume orthogonality, but also normalization here. Like I said, if the basis is orthogonal, then it's very easy to normalize each vector and assume that the basis is orthonormal. But once you have that, then for any vector v in your vector space, you can write this expression and it would hold true. So you have coefficients accompanying each vector in your basis, and those coefficients are simply given by the inner product of v with the corresponding vector in your basis. Okay, and so in that sense, what this means, what each of these coefficients represent, it's simply the projection of v in the direction of v1 in this case, and here v in the direction of v2, and so on and so forth. Geometrically, what this is telling us is, let's say we have two basis vectors e1 and e2, then the our vector v is this vector here, the long one, and then the projection of v in the direction of e1 is given by this inner product of v with e1, and this length here is v with this should say e2. This is the projection of v in the direction of e2. Now, algebraically, what this means is, for example, suppose that our vector is v and it's 7, 3, for example, no particular value in that specific vector. So then 7, 3 can be written in terms of e1 and e2 by choosing coefficients a1 and a2. And if we suppose we pick this basis e1 and e2, also shown here, to be in particular the basis we were playing with before. Suppose this is the basis in our two-dimensional system, two-dimensional problem, and so then you see that calculating a1, the coefficient that goes in here, amounts to calculating the inner product of v with e1, and if you follow that calculation, it will give you 10 divided by square root of 2, and the inner product of v with e2, again, it will give you, if you follow the calculation, it will give you 4 divided by square root of 2. So let's do this first one, v with e1. How does that go? Well, we have to do 7, 3 multiplied by our vector, e1. Okay, so 7, 3 multiplied by this is going to give me 7 divided by square root of 2 plus 3 divided by square root of 2, and that's our 10 divided by square root of 2. And the other one is going to be 7 divided by square root of 2 plus minus 1 over square root of 2 times 3. And so that's going to give us 7 minus 3 all divided by square root of 2. And that's why I get at the bottom here 4 divided by square root of 2. So these are the examples involving conventional vectors, but what about examples in spaces of functions? So let's take as an example the example that I usually like to use, which is taking V to be the space of all possible linear combinations of some monomials. And so what we have here is a space of polynomials. It will be a space of polynomials up to degree 3. And I'm going to take that vector space and attach to it this inner product f comma g defined by the integral between -1 and 1 f of x, g of x, dx. So clearly, using that definition of inner product, I have an inner product space. It's a 4-dimensional space, and this is clearly a basis. It's linearly independent. It's a set of linearly independent vectors, and they generate V by definition using linear combinations. And so now I am able to analyze the inner product of these vectors with each other and see if I have indeed an orthogonal basis or not. And at first things start to look pretty good. I do the inner product of 1 with x, so this vector with this vector, and I follow the calculation, minus 1 of 1 of x. But and this calculation gives me x squared divided by 2. That's a simple integral, and that gives me 1/2 minus 1/2, which is 0. Okay. Then I go on and I see, oh, this is great. The integral between minus 1 and 1 of x times x squared gives me the integral of x cubed. And if I do the integral, I get 0 again. But things are not so rosy later on. You see that to begin with, we see that this basis is not normalized. The integral of 1 with 1 is 2. The integral of x with x is 2/3, so it's not normalized. Okay, that's not a big deal. I could normalize the basis by dividing the vectors by the square root of the magnitude. But there's a bigger problem, which is that the integral between minus 1 and 1 of x with x cubed, which are two different vectors, is non-zero. So in fact, it's 2/5. So it tells me that the basis that we have here is not orthogonal. Okay, let me go back to the top here. So this is an example then of a basis that is a well-defined basis, is linearly independent, and by definition, it generates the space that I want. But with this inner product, this basis is not orthogonal. I'm able to normalize these vectors to whatever I want by dividing by constants in each case, but I see that they're not orthogonal. They're not all orthogonal to each other. Some of them are. One is orthogonal to x is orthogonal to x squared, but x is not orthogonal to x cubed. And so I have to do something about that. As I was saying, then we may normalize the vectors in this way just by dividing by a constant. That means the 1 will be replaced by 1 over square root of 2, x will be replaced by x divided by square root of 2/3, and so on, but the basis will remain not orthogonal. And so I would have to do something about that if I want an orthogonal basis for that space. So what do we do if we want that? We can find one, and the answer to that is called the Schmidt process. And it's possible by that process, if you start with an orthogonal basis like we started here, like linearly independent, well-defined basis that we start here, it's possible to get an orthogonal basis based on these guys if you follow that process. And we'll see that in a future video. It's a simple algorithm where you take one vector and you grab another vector and you start orthogonalizing them as you go, and then you consider them one at a time. And at the end of the day, if you did everything correctly, you end up with another basis with the same number of vectors, but now it's orthogonal. So finally, I want us to consider another example in the space of functions. This is a space generated by the functions sine of t, sine of 2t, sine of 3t, and so on and so forth, in principle up to infinity. And consider this inner product f with g defined by the integral between minus pi and pi of f of t, g of t dt. It's not difficult to see, and I'll leave this as an exercise, but the integral between minus pi and pi of sine of nt and sine of mt is 0 if m is different from n. Okay, so in this example, m and n would be 1, 2, 3, and so on and so forth, and this will vanish if m is different from n. Of course, if m is equal to n, then these two become the square of sine of nt, and it will be non-zero. Oh, I missed the dt here. There should be dt here. But what this means is that this basis is orthogonal. Okay, so the space generated by these vectors is an infinite dimensional vector space, and these functions are orthogonal to each other. So these are very important functions. It turns out they are part of the Fourier basis, which is essential for Fourier series. It's not the whole story. Notice that I didn't write the cosines. The cosines will be part of the story here, will be part of the game, but this is at least part of it, and we will see that in a future video. That's all I have for you today. I hope you enjoyed this video, and if you find this series helpful, please consider liking and subscribing. It would really help the channel. And I also want to say, if you're not a UNC student, but you're looking for a tutor in physics or math, in English or in Spanish, then you can contact me at shorttext331@gmail.com or leave a message in the comments section below. Until next time.